Good morning, everyone. I hope everybody's had a fantastic week and everybody's still doing good. Happy Friday, another week down the tubes. Today we're looking at lesson 30.19, which is an introduction to the Bohr model of the atom. And this says part A because we're going to continue this in the next lesson. This lesson can be found on page 14 of your current lesson handout. Remember that one of the main problems to Rutherford's model of the atom, which is called the planetary model or the nuclear model, is that it cannot explain atomic line spectra. And we talked about this in the last lesson, but today I want to focus on the hydrogen gas spectrum of light. So when you heat up hydrogen gas, it turns out that it emits only four very, very specific colors. We call that the bright line spectrum. So at the top of the screen, what we are looking at is the bright line spectrum for hydrogen. And there's a wavelength of 410 nanometers that is emitted by hydrogen when you heat it up. There's one of 434 nanometers, 486, and 656. You might wonder how we know the wavelengths. Basically, what you do is you pass the light through a diffraction grating and measure the angle that each of these colors is producing a bright line at, and you use the formula lambda equals d sine theta over n. If we were in class, we would do this experiment. We would take a diffraction grating, we would shine the light from the hydrogen gas discharge tube through the diffraction grating, and we would measure the angles and do some quick calculations. And it's a great little lab because you get these numbers. These are not just some numbers you see in a textbook. These are numbers that you measure in the laboratory. So it's a little disappointing that we can't do this. You can see at the bottom, by the way, there's the absorption spectrum for hydrogen, which would be what you would observe if you allowed every wavelength of light from a hot, solid, glowing object to pass through cool hydrogen gas. The cool hydrogen gas would swallow up or absorb those four wavelengths. And I just put the dark line spectrum there so that we could remind ourselves that the wavelengths that are emitted by an atomic gas are exactly the same as the wavelengths that the atomic gas can absorb. And going back to Rutherford, Rutherford can't explain this. Well, Niels Bohr came up with a way to explain it. And his theories are also able to explain the spectra of some of the other atoms, but not all of them. If you're a chemistry kind of person and you look at your periodic table, anything in group 1A is explainable with Niels Bohr's theories. So hydrogen, potassium, sodium, I don't have it in front of me, rubidium, cesium, I don't know what else there is, but in the very first column of the periodic table, all of those elements, all of those atoms have one electron in the outer valence shell. And because of that, Bohr's theories can explain that. I'm mentioning this because eventually what we're going to say is Bohr's model of the atom is no good when it comes to most atoms. The basic idea involved with Bohr's model of the atom is that electrons can exist in energy levels that are quantized. And what this means is an electron is allowed to have a particular energy, and an electron is allowed to have a different energy, but it's not allowed to have energy values in between. Kind of like when we say the charge on an object has to be quantized. The charge of an object has to be one elementary charge or two elementary charges, but it cannot be a number in between those two values. The same thing is true for electrons in atoms. When an electron moves from one energy level to a lower energy level, the electron loses energy. And if the electron loses energy, we say the atom loses energy. Where does that energy go? It goes into the production of a single photon. So whatever the amount of energy is that the electron loses when it, quote, falls to a lower energy level, that amount of energy is exactly equal to the energy that the photon is emitted. When an electron moves from one energy level to a higher energy level, it has to absorb energy. When things gain energy, the energy has to come from somewhere. And usually where this comes from is that a photon is absorbed. So when a photon strikes a hydrogen atom, if the energy of that photon is exactly equal to the energy change that the electron can go through in the atom, then the photon will be absorbed. Now, both of these ideas explain these spectra. Why is it that a wavelength of 656 nanometers is absorbed or emitted by hydrogen? Well, that's because 656 nanometers corresponds to a particular photon with a particular energy. And the reason why that photon is emitted is there happen to be in hydrogen two energy levels which have a difference equal to the energy of that photon. So an electron in an atom can lose exactly the same amount of energy as that 656 nanometer photon, in which case the photon will be emitted. On the other hand, if the electron is at a lower energy level, it is possible for the electron to gain an amount of energy exactly equal to the energy of that 656 nanometer photon, in which case that photon can be absorbed. And the same would be true of any of these photons. So here's a diagram of a Bohr model of the atom. Because we're drawing circular orbits here, we're borrowing an idea from Rutherford, and sometimes when you see an atom drawn this way, it's called the Rutherford-Bohr model of the atom. Bohr, by the way, is not interested in the particular orbits or motion of the electrons. Bohr is interested in the energy the electrons have. One final comment about this simplistic diagram. Those are the first 4 energy levels, but there are many energy levels. In fact, mathematically, an infinite number of energy levels within any atom. So if you have an electron in the first energy level, and I've drawn the electron quite large, and if this is hydrogen, then the red dot in the center is a proton, because hydrogen has a proton in the nucleus. The electron is existing in some kind of state in orbit around that proton. I drew the electron quite big so that you could see it. The electron is allowed to be in the second energy level. So the electron is allowed to go from n equals 1 to n equals 2, but it is not allowed to be in between, which is a bit of a strange idea, but it's true. The electron can go from the second to the third. By the way, the electron can go from the first to the third. The electron can dance around from any one energy level to any other energy level. And the electron can be in the fourth energy level. And the fifth and sixth, but I'm only drawing up to 4. So to summarize this, I've got 2 diagrams here with some energy levels in a hypothetical atom. The first thing I want to draw your attention to is the bottom energy level, which is the n equals 1 energy level, is typically called the ground state. And the infinite energy level, the energy level at the very top of any atom's energy level diagram, is called the ionization state. And in any energy level diagram for an atom, the higher the electron is in the energy level diagram, the more energy it has. So on the left-hand diagram, if we have an electron that makes a transition from the 5th to the 3rd energy level, the atom loses energy because the electron loses energy. And that means a photon is emitted, spit out. If we want to cause an electron, I'm looking at the right-hand diagram now, if we want to cause an electron to move from the 2nd up to the 6th, then a photon must be absorbed. Again, the photon that is emitted or absorbed has to be exactly the right amount of energy because the electron is not allowed to be in between these states. Incidentally, it's called the ionization state because if you can get an electron to that location, then it will be free of the atom. So we have some questions now. An electron in an atom drops to a lower energy level. The initial energy level was 2.24 electron volts higher than the final. What happens when the electron makes the transition? Well, if the difference between the two energy levels was 2.24 eV, and the electron moves to a lower level in this process, one of the things that happens is the electron loses 2.24 electron volts. Since the electron is part of the atom, it's fair to say that the atom loses 2.24 electron volts of energy. Since the atom loses that energy, there must be a photon emitted. And since E equals hc over lambda for a photon, we can calculate the wavelength by taking hc over the energy. I can take 1242, which is hc in electron volt nanometers, and divide by 2.24, and we get 554 nanometers. So that means a 554 nanometer photon is emitted. It's probably green, although we won't worry about the exact classification. Number 2, an atom absorbs an 850 nanometer photon. Explain what happens within the atom. Well, the first thing I would like to do is find the energy of that photon by taking 1242 divided by 850. This will be electron volt nanometers divided by nanometers. By the way, 850 is infrared. We get 1.46 electron volts. So what happens in the atom is the electron gains 1.46 eV, which means the electron rises to an energy level 1.46 eV higher than where it started. Number 3, an atom can emit a 120 nanometer photon. What does this tell you about the structure of a particular atom? Well, if we take 1242 divided by 120, we get the photon energy in electron volts. In case you haven't picked up on this, we're always focusing on energy here. 1242 divided by 120, and by the way, I hope you can see why that 1242 is a very important tool. 10.35 eV is what you get. So I'm not going to write down the answer to this question. I will just tell you what that tells us about the structure of the atom is that there are two energy levels within the atom that are 10.35 electron volts apart. I don't know anything else about the atomic structure. Those two energy levels could be the 2nd and the 11th, or the 1st and the 3rd. But what we do know is there are two energy levels that are exactly that far apart, because if there weren't, that photon would never be emitted by the atom, because the photon energy has to exactly equal the change in energy of the electron within the atom. Number 4, why should the emission line spectrum for hydrogen contain only 4 visible lines? Well, you're going to have, as part of your assignment today, an exercise which will drive this home. But basically, if you start subtracting energy levels using hydrogen's energy level values to find the energy of all the different photons that hydrogen can emit, you're going to discover that there are a whole bunch of photons with wavelengths smaller than 400 nanometers. So there's a whole bunch of transitions within hydrogen that produce ultraviolet energies. You're also going to discover that there are a whole bunch of differences of energy levels within hydrogen that correspond to energies of infrared photons. But when you start subtracting all of the different energy levels within hydrogen to find out differences between pairs of energy levels, you'll discover only 4 of those energy level differences correspond to visible light photons. And I don't know if you remember, it was quite a while ago, but when we first learned about electromagnetic radiation, one of the things I told you was that infrared, ultraviolet, and visible light are always produced by electron transitions within atoms. Number 5, describe the electron transition in an atom so that the photon with the shortest possible wavelength is emitted. Well, the shortest possible wavelength corresponds to the most energy. The energy of a photon is inversely proportional to the wavelength. And the only way we're going to get the biggest, most energetic photon coming out of an atom is if we have the electron in the atom fall from the ionization state all the way down to the n=1 state. So the electron transition would be the electron falls from the very top all the way down to the ground state. And 6, how do the wavelengths and frequencies of the photons in these two diagrams compare? Well, when we take a look at the diagram on the right, there's a larger energy level change. So on the right, we are dealing with more energy than we are on the left. And we're back to the idea that energy is proportional to frequency, which means the frequency of the photon absorbed on the right is more than the frequency of the photon emitted on the left. But because the energy is small on the left, the wavelength of the photon emitted on the left is bigger than the wavelength of the photon absorbed on the right. Now we're going to do some examples specific to hydrogen. And I've decided that I'm not going to spend any time explaining to you where this information comes from, but in our shared classroom folder, you will discover there is a file, and the name of the file is Bohr Hydrogen, and it shows the energy levels for hydrogen from E1 up to E7, and then it has 3 dots, and that just means there's an infinite number of energy levels in between. And it's a 2-page document. When you take a look at the difference between E1 and E2, it's quite large. Don't worry about the numbers just yet. But there's a huge energy change from the first energy level in hydrogen to the second. And we're not worried about where these numbers come from. We don't have time for that. When you take a look at the difference between the second and the third, it's less. And between the third and the fourth is less and less and less. It keeps decreasing. So it's important that you understand the energy change from 1 to 2 is huge. Now, why do I have 2 pages? If you take a look now at the values, E1 on page 1 of this handout is negative 13.6. And I want you now to take a look at E infinity. It's 0. So how many electron volts would I have to add to negative 13.6 to get 0? The answer is 13.6. For me to go from the first to the infinite energy level would require adding 13.6 eV. Now, when you take a look at the second page, the numbers are different. But the bottom number now is 0 and the top number is 13.6. And what is important is we are only ever concerned with the difference between the energy levels. That's all we care about. So we can either label them by starting at 0 on the bottom and going up, or we can start at negative 13.6 on the bottom and go up. The differences between the energy levels will be the same. So if you took, looking at this energy level, E5 minus E4, 13.056 minus 12.75, and then you looked at page 1 and took E5 minus E4, negative 0.544 minus negative 0.850, you'd get the same thing. So we are going to be referring to this whenever we're doing the examples for the rest of this lesson. What is the wavelength of the photon emitted when an electron falls from the 7th to the 3rd energy level? I have a preference. I prefer to use the energy level diagram that has the negative numbers. When we find the change in the energy of the electron with any of these examples, you always take the upper energy and subtract the lower energy. Whether the electron goes up or down, it doesn't matter. So the change in the energy of the electron will be E7 minus E3, which is negative 0.278 eV minus negative 1.511 eV. And get 1.233 electron volts. This 1.233 electron volts is both the loss of energy of the electron and the energy of the photon. So this is equal to hc over lambda. And we've done these calculations so many times, really it should be pretty second nature for you to just understand that you're going to have to do this calculation to find the wavelength in nanometers. (1242) divided by my answer. So we are talking about 1007 nanometers, which is infrared. Number 2, what is the minimum wavelength of light? Well, remember, the minimum wavelength of light corresponds to the most energy. And remember, we're talking about a change in energy. So the only way the electron can lose as much energy is if the electron goes from E infinity all the way down to the ground state E1, which means we can take E infinity, the upper energy, minus E1, the lower energy, which is 0 minus negative 13.6 eV, which is 13.6 eV. Now we can do the 1242 trick. (1242) divided by 13.6 gives 91 nanometers. So the shortest wavelength of radiation that hydrogen can emit is a 91 nanometer UV ultraviolet photon. By the way, there's a reason why the negative numbers are in the energy level diagram, but we just can't get into why because of our time limitations here. If you're more comfortable using the other side of the page, page 2 of your energy level diagram, that's fine. You would just have here, for E infinity, you would have 13.6, and for E1, you would have 0. You would still get this 13.6 eV as the difference. Number 3, in a hypothetical atom, there are 5 energy levels. How many different photons can the atom emit or absorb? Well, we're just looking at how many different pairs of energy levels there are. Let's talk about emission. The atom can have an electron that goes from 5 to 4, from 5 to 3, from 5 to 2, or from 5 to 1. The atom could have an electron that goes from 4 to 3, 4 to 2, or 4 to 1. It could have electrons that maybe go from 3 to 2 or 3 to 1, or it could have an electron that goes from 2 down to 1. So if we count all of these different pairs, these different transitions, I have 4 red plus the 3 green, which is 7, and then 8, 9, 10, we get 10 transitions. So the answer to this question is 10 different photons. There is only one reason why I use this example in my lesson, and that's because I also teach Math 30-1. And I can point out to those of you that have completed Math 30-1 that what you're talking about here is you have 5 energy levels, and to produce a photon, you need to choose 2 of them. And if you calculate 5 choose 2, you get 10. Now, those of you that are taking Math 30-1 right now, this is also going to be useful because when we learn about this in a couple of weeks, I'm going to be able to point back to it and say, there's an example of how we could have used combinations, which is what this is, to find an answer to a problem outside of math. I just like to have a connection here between math and physics. Your assignment is question 1. Now let me explain question 1 to you. You have to use the energy level diagram that's in the shared folder to fill in this chart. So let's talk about the very first entry, which is this one. How are you going to fill that entry in? What that is saying is we have an electron in hydrogen that goes from an upper energy level of 2 down to a lower energy level of 1. And the question is, what is the wavelength of the photon emitted? So you would go to your energy level diagram. So because the electron goes from the second to the first energy level, I need to take the upper energy of negative 3.4 and subtract the lower of negative 13.6. This energy is the energy of the photon that's emitted. So now I'm going to go back to our problem. If I want to find out what to put in this first entry when it goes from 2 to 1, I know the photon has an energy of 10.2 eV. I need to take 1242 divided by that. And this is my answer. It's 122 nanometers. So in your chart, you record 122 nanometers. I would also like you to record what type of radiation it is. Remember, visible light is from 400 to 700. So less than 400 is ultraviolet, more than 700 is infrared. So for example, when you do 5 to 4, you're going to discover that you get 4,059 nanometers, and that's infrared. For some of these, you're going to get visible light. And if you get visible light, I want you to try to identify the color. And by the way, if you're really following everything and how it's connected within this lesson, you should realize there's only going to be 4 of these that are visible light, because there are only 4 visible lines in the emission spectrum for hydrogen. Anyway, that's your assignment. I would like you to work through that. It will only take you about 10 minutes. You're subtracting energy levels, setting that energy you get equal to hc over lambda, and calculating the wavelength. I hope that you have a wonderful weekend, and we will see you on Monday. Talk to you later.